Hello and welcome to this Revision Monkey video on the Chemistry Paper 2 required practicals. The first three required practicals, paper chromatography, rates of reaction and the analysis and purification of water, are all for combined scientists, and at the end I'll go through the last required practical, identifying ions, which is for separate science only. Paper chromatography required practical. We use paper chromatography to separate coloured substances. So in this practical, you may be asked a question similar to the one above that says, do food dyes A and B contain chemicals that are in band dye X? So in this practical, we're going to separate three dyes, A, B, and another one called X, and we're going to compare the patterns at the end of the practical. In your exam, they might not talk about food dyes, they might be talking about inks or another random coloured substance, but the process is exactly the same. What you need to do to start off with is draw a horizontal pencil line around 2 centimetres from the bottom of a piece of chromatography paper. Do not use pen, as this will smudge and spread up the paper. Pencil is insoluble, so will not dissolve in the solvent. So this line here that we draw on must be drawn in pencil. On the pencil line, put a small dot of the dyes that you want to separate and label these with pencil underneath. So I've labelled them A, B and X. Place the chromatography paper in a solvent, for example water. The solvent must be below the pencil line. Put it in a beaker with a lid to prevent the solvent from evaporating. Then we leave until the solvent front nearly reaches the top of the paper, then remove the chromatography paper and leave to dry. So the process of separating a substance through chromatography has two different stages. The paper itself is called the stationary phase, and when the inks are dissolved in the solvent, that is called the mobile phase. And within the inks that you've put on the paper, you will have different compounds, and they will interact differently with the paper, and they will have different solubilities. So they will spend different times attached to the paper in the stationary phase, and different amounts of times dissolved in the solvent in the mobile phase. So you'll end up separating the substance as it moves up the paper. And to do that, what happens is the solvent moves up the paper, and when it hits the dyes, it dissolves any of the soluble compounds in the dyes. They will then be carried up the paper in the mobile phase, and depending on their solubility, they will stop at different distances up the paper. I mentioned earlier the solvent front. That is where the solvent finishes as it goes up the paper. So if the solvent is moving up and it gets close to the top of the paper, where it reaches here is called the solvent front. And when it gets near to the top, we will then remove the paper and leave it to dry. So the pattern left on the chromatography paper is called a chromatogram. So after we've left it to dry, we will see several dots of different colours on the piece of paper. We would then compare the chromatograms of dyes A and B with the chromatogram of the band dye X. In your exam, you're likely to see a chromatogram in black and white like this, rather than it being printed in colour, and each dot just shows how one of the colours is separated as it's gone up the page. So you can see here dye A has 2 dots and so has dye X, and this top dot here is in exactly the same position as the one on X, suggesting it could be the same compound. Now you'd want to investigate this further to see if dye A does contain one of the chemicals that is in the band food dye X. Because we've only tested this so far on one solvent. We chose the solvent as water. But to be absolutely sure that our food dye contains a banned chemical, we would need to repeat this in different solvents, for example, maybe ethanol. And if this compound in A matched X in different solvents, it's highly likely that it is containing that banned compound. We can't just be sure if we just use one solvent. We must repeat it with different solvents to be absolutely sure. In different solvents, Different compounds will spend different amounts of time in the mobile and stationary phases, and what we'll talk about later is the fact that they can have different RF values. The position of this colour on dye A does not match that of dye X, and you can see for dye B it only has one colour here, and it doesn't match at all with dye X. Now, because dye B's got one colour and one colour only, this tells us that dye B is a pure substance because it only contains one compound. In the exam, you might be asked to calculate an RF value. You do this by calculating the distance travelled by a substance divided by the distance travelled by the solvent. This top line here is representing the solvent front, which is where the solvent got to before we took the paper out of the beaker. And I'm just going to show you an example using one compound here that we found on our chromatogram. Now, the important thing is when you're calculating the RF values, you must calculate it from the centre of the dot on your chromatography paper. Not at the top, not at the bottom, but right in the middle of the dot that you're using. And the baseline that we're using is our pencil line where the dye started. So we need to measure the distance travelled by the substance, so this distance here, and then the distance travelled by the solvent. So let's say, for example, the distance travelled by the substance was 400 millimetres and the distance travelled by the solvent was 500 millimetres. Then we do 400 divided by 500 to get us an RF value of 0.8. As I alluded to previously, RF value will be different depending on the solvent used. So this could be, for example, the RF value for water for this particular compound, but if the solvent was ethanol, then this number here would be different. Rates of reaction required practical. When wanting to calculate the rate of a reaction, you might need to use one of these two equations. The first one says the rate of reaction can be calculated by the amount of reactant used up over time, and the second one is the amount of product made over time. So we're going to design some investigations using these two equations. Now, there are several factors that you may be asked about in the exam that affect the rate of reaction. Those include temperature, concentration, and surface area. So you may well be designing an experiment and changing any one of these three things. So that would be your independent variable. And if you change temperature, for example, you need to keep concentration and surface area of your reactants the same. And the same goes if you are selecting a different independent variable. One of them you change and the other two you have to keep the same. There are several different practicals that you can do to calculate rate of reaction, and any one of these may come up in the exam. So this first one focuses on the amount of product made over time, and the independent variable that we're going to change is concentration. So we'd measure 50 ml of 0.1 molar hydrochloric acid using a measuring cylinder and pour it into a conical flask. We'd place, for example, 1 centimetre of magnesium into the conical flask, attach a gas syringe and start a timer. So in here we'd have our acid and our piece of magnesium, which you should know is going to create hydrogen gas. To calculate the rate of reaction in this experiment, we could record the volume of gas produced at regular intervals, for example, every 30 seconds for 5 minutes. And as gas is produced by the reaction, the gas syringe will move outwards and you can measure the volume of gas produced. Do not write amount, you must use the word volume. Then we would plot the volume of gas produced against time on a graph, and we can use this to calculate the mean rate of reaction, and I'll go through how we do this later on. We then repeat the experiment for the following concentrations of acid. So this will be our independent variable, the concentrations of acid. The dependent variable would be our volume of gas, which we then turn into our rate of reaction down here. And important control variables are things such as the volume of acid that we are using, the length of magnesium that we're using, and things such as temperature as well. As in all experiments, it's also really important to talk about the fact that you're going to repeat the experiment 3 times and calculate a mean for each concentration of acid that you're using. So a different practical setup now, but still looking at how concentration affects the rate of reaction. This time, this focuses on the equation, the amount of reactant used over time. So we start off by placing a conical flask on a balance and zeroing the balance. We would then measure 50 ml of 0.1 molar hydrochloric acid and pour this into the conical flask. And we then place 1 centimetre of magnesium into the conical flask and start a timer. We take the initial reading on the balance as well, so we're starting off with a mass of 25 grams. Now again, we're using magnesium and acid, so we're producing a gas, and because we have no bung on the conical flask, that gas is going to be allowed to escape out of the conical flask, and in doing so, because mass is escaping from the system, the reading on the balance is going to go down. So to calculate the rate of reaction, we can record the mass on the balance every 30 seconds. So we'd wait 30 seconds, write down the new mass, another 30 seconds, again writing down the mass, and so on, and so on. And then we plot the mass against time on a graph, and we can calculate the mean rate of reaction. We'd repeat this experiment for the following concentrations of acid: 0.5 molar, 0.7 molar, and 1 molar, and as always is good practice, right at the end that you're going to repeat it 3 times for each concentration and calculate a mean. A third practical that you might see in your exam, again answering the same question with changing concentration and measuring the rate of reaction, is when you draw a black cross on a white tile or piece of paper and place a conical flask on top. We'd measure 50 ml of 0.1 molar hydrochloric acid using a measuring cylinder and pour that into the flask. And we'd also measure 50 ml of sodium thiosulfate using a measuring cylinder and pour that in the flask as well. So you can see at the moment when we've put the acid and sodium thiosulfate in, we can still see the cross because the solution is colourless. However, gradually over time, a precipitate will form to make the solution go cloudy, and at that point we will no longer be able to see the cross. So you can see now, when the solution has gone cloudy, we can no longer see the cross, and we then record the time it takes for the cross to completely disappear. Obviously this is subject to error because different humans will have a different opinion on the exact time that the cross has disappeared. We'd repeat the experiment for the following concentrations of acid: 0.5, 0.75 and 1 molar. And for this one, because we're not measuring the amount of reactant used or the amount of product made over time, we're simply looking for the time it takes for a colour change, we could use the equation rate equals 1000 divided by time to calculate a rate of reaction for each concentration that we're using. So with the results of a rate of reaction experiment, you may well be asked to draw a graph or do some calculations using a graph that's provided to you. So let's look at this graph here first of all. This might be a graph that we might have drawn from the first experiment, whereby we were measuring the volume of gas produced over time. A few things about rate of reaction graphs to start off with then. The steeper the gradient, the faster the rate of reaction. So you can see this first section here is really steep. Then a shallower gradient here, so the rate of reaction is slowing down. And at this point here, where the graph starts to level out, the reaction has actually stopped. And we know that because if you read off the graph here, no more gas is being produced. So here are some common questions that you're asked. One here says, what is the mean rate of reaction? So to calculate this from the graph, you would find out the point where the reaction stopped, draw a line from the x-axis up to that point, and then a line across to the y-axis, and you would read off from the bottom the time that it took, so 15 seconds, because from 0 to here is 15 seconds, and the volume of gas produced in that time, from the 0 up to here, so 34 approximately. And then we would calculate that by doing 34 divided by 15, giving us an answer of 2.3 centimetres cubed per second. We always do the y divided by the x in our calculations, and we get the units for rate by reading them off the graph. Centimetres cubed divided by seconds is what we've done, so those are our units. They could also ask for a mean rate of reaction for a particular time point. For example, what is the mean rate of reaction between 4 and 12 seconds? And in that case, at time point 4, you draw a dotted line up and across to the y-axis. You do the same for 12, and then you would read off between those two sections. So between 4 and 12, we've got a time of 8 seconds. And between our two markers on the y-axis here, we have a volume of gas produced of 12.5 centimetres cubed. So to calculate the rate of reaction, again, we do the y divided by the x. So our y value is our 12.5 divided by our x value of 8 seconds. 12.5 divided by 8 gives us, for that section of the graph, a mean rate of reaction of 1.6 centimetres cubed per second. And finally, a calculation for higher tier only. So if you're doing foundation, you can skip to the next required practical. This one says, what is the rate of reaction at 8 seconds? So this is exactly at this time point here, what is the rate of reaction? And to do that, you need to draw a tangent on your graph, which is a straight line as close to the line as possible at that point, like the one I've just drawn on there. Now there will be some leeway in your exam, but try and get it as close as possible and following the same pattern as closely as you can. And then look on your gradient line where the line crosses the grid at some sensible points. For example, here it crosses in the corner and down here. Then we draw dotted lines to make a triangle between those two. And again, we're going to do the change in y, which is this bit, divided by the change in x to calculate our gradient. So we do 15 divided by 10 to calculate the rate of reaction at that exact point as 1.5 centimetres cubed per second. Analysing and purifying water required practical. For this practical, there are 3 different things that you might be asked to write about. The first one is testing the pH of water samples to see if they are in the potable range. The second one is to test the water samples for dissolved solids. Do they have a low enough amount of dissolved salt to make them potable? And finally, if they are not potable, how can we use distillation to purify the water sample? So the first 2 relate to analysing the water, and then the distillation refers to purifying the water. So looking at the first step then, testing the pH of water samples, we would use a device called a pH meter, or sometimes you may see it called a pH probe, but a pH meter is best. All you do with the pH meter is put it in your sample, and then it will give you a reading of the pH digitally. So I've got 3 different samples here. I've got some rainwater, some spring water and some seawater. And I put my pH probe in the rainwater, and I would then record the pH in the table. Repeat that with spring water and record the pH, and finally with seawater and record the pH. Now, are they in the potable range is the question that we're looking at. Are these safe to drink? Well, the potable range is between pH 6.5 and 8.5. So you can see here that the spring water and the seawater in these examples are within that pH range, so they could be potable, but the rainwater is too acidic. Okay, it falls below that pH range, so it is not considered to be safe to drink. But we don't yet know if it's potable or not, because it also has to have a low enough amount of dissolved salts and, of course, a low enough amount of microbes. The second part is then testing the water samples for dissolved solids. So we're going to look if they have a low enough amount of dissolved salt to make them potable. This is the equipment that we are going to use. We have a balance here. We've got our Bunsen burner on a heat-proof mat with a tripod and gauze. And then we have a beaker, and this beaker is just acting as a water bath. It's just full up with tap water, and on top of that you've got an evaporating dish, and that is where you are going to put your water sample in your evaporating dish. All this water is doing is just acting as a water bath that will gently heat the evaporating dish. It's much better and much safer to do it this way rather than putting the evaporating dish straight upon the gauze. You can also get electronic water baths that will do this as well, which you may see in an exam. So the method for this, we are testing to see if this water sample has dissolved solids in it. So we're going to record the mass, hence the balance, of an empty evaporating dish. We are then going to measure 5 millilitres of one of the water samples, for example rainwater, using a measuring cylinder and add this to the evaporating dish. So we pop our small amount of water in our evaporating dish like so. We then heat gently over a water bath until all the water evaporates from the evaporating dish. Now, to do it safely in the lab, what you might do is allow most of the water to evaporate and then leave the rest to evaporate slowly. But once the water evaporates, you'll be left with none in your evaporating dish. And you will allow that to cool and then re-weigh the evaporating dish. You would then record any mass change of the evaporating dish, if there is any, and observe any salts left on the evaporating dish. So once the water had evaporated, if your sample contains salts, it would likely that you would see salt deposits building up on the sides of the evaporating dish. So when you were to put that dish back on the balance and re-weigh it, you'd expect it to be heavier because it now has salt on it. You would then repeat steps 1 to 6 with the other water samples, for example if we used salt water and spring water. So when you look at your results, just because one of the samples may have a low amount of dissolved solids, a low amount of dissolved salt in this case that we're looking at, it might not mean that it is still potable, even if it passes the pH test and the low amount of solids. You would have to make sure that it has a low enough amount of dissolved microbes. So if your water samples are not potable, you can use a process called distillation to purify the water sample. I've just used a different colour here just so we can make it obvious, but let's suggest that in here we put our salt water, because this is what many countries, such as Saudi Arabia, would do because they don't have much rainwater. And this will allow them to access drinking water from their normally non-potable salt water. So the flask that we put this in is called a round bottom flask, and you would heat that flask normally using a water bath or perhaps using a Bunsen burner if you're doing it in the lab. You have a thermometer at the top here, which you'd want to make sure for pure water was reading 100 degrees C, so that you know that in your beaker over here you are getting pure water. So as you heat the salt water, the water will evaporate and it should leave any salts behind in the round bottom flask. The water will evaporate and it will turn into water vapour and it will go up the tube here. This piece of equipment here is called the condenser, or you might see it written as the condensing tube. So the condenser is kept cold by this cold water going in and around the glassware. It doesn't mix with what's in the middle, it just goes around the glassware to keep it cool. And as the water vapour comes in here, it is then condensed into a liquid and then it will collect as pure water in the beaker. So in this purification process, we would test the pH of the water using a pH meter. We would neutralise it if we needed to by adding alkali if it's acidic or adding acid if it's an alkali. And we use a pH meter, not an indicator, to determine when it's neutral. Because if you're trying to purify a sample, there's no point adding an indicator like universal indicator in there because you're just contaminating it. And a pH meter is going to give you a much more accurate result. So then we pour the salty water into the distillation apparatus, and we said specifically it's the round bottom flask it goes in, and we heat it. And the distillation process, as discussed, will leave us with pure water in our beaker, and we would then just retest the pH at the end to check that it is neutral. If you're doing separate science, there could be an addition to this practical whereby you have to test the water for salt as well before you start. Now, salt is sodium chloride, so this links into the last required practical that we'll talk about in testing for ions. Because if we wanted to test the water for salt to start with, we'd need to test the positive ion, which is sodium, and the negative ion, which is chloride. So to test for sodium, we would take a small sample and do a flame test, and a yellow flame will indicate the presence of sodium ions. And for the chloride ions, we would test for chloride ions by taking a sample and adding a few drops of dilute nitric acid and silver nitrate solution. A white precipitate forming would indicate the presence of chloride ions. So this, in addition, I would recommend you write about doing before and after the distillation of salty water. Identifying ions required practical for separate science only. In this required practical, there are lots of different tests to remember for different ions. So why would we need to test for ions? Well, if we had this unknown compound here, we would be able to do a variety of tests to identify exactly what that compound was made of. So this is the type of question you might be asked. Describe the test you would carry out to identify the ionic compound. Remembering back from paper 1, ionic compounds are metals and non-metals bonded together. So for example, you could have calcium sulfate. Calcium ions are the metal bonding with the sulfate ions. You could have sodium chloride, or magnesium carbonate, magnesium bromide, potassium iodide, or copper sulfate. So there's so many different ones that you could have, and these are just a few examples. With this compound, we have no idea, apart from the fact that it's white, we have no idea what it's made up of. So you're going to have to do a variety of tests to work out what the positive ion is, and we call this the cation, and what the negative ion is, and we call this the anion. Once you've worked out what both things are, you can then name the compound. So first of all, let's go through the test for cations, which are the positive ions. One thing that you can do to test for the metal ions, which are the positive ions, is to do flame tests. You'd need a wire loop made of an unreactive metal, for example platinum, and you'd need to clean the loop by dipping it in dilute hydrochloric acid and then putting it in a blue flame until it burns without any colour. You then allow the wire to cool and then dip it in the sample that you are testing, for example the white powder from the previous page. You'd then put your loop with your unknown sample back into a blue flame. If the flame was orange-red in colour, that would indicate the metal ion was calcium. If the flame was yellow, that indicates sodium. If the flame was crimson, that would indicate lithium. A lilac flame would show you'd have potassium, and a green flame would show you that the cation was copper. Flame tests, however, are not the only test that can be used to identify cations. There is another test whereby you add sodium hydroxide to your unknown ionic compound. So we've got a conical flask here, or can use a beaker or a test tube, and you have sodium hydroxide and your unknown powder inside. A precipitate will form, and that's because you will make an insoluble hydroxide. So precipitate is a solid that's suspended in the solution because this hydroxide does not dissolve. The colour of the precipitate will then help you identify the cation. If a blue precipitate forms when you add sodium hydroxide, you have identified copper in the compound. If a green precipitate forms, you've identified iron 2, and the 2 just means you're talking about Fe2+, remembering that transition metals can make ions with different charges, because Fe3+, or iron 3, makes a different coloured precipitate. So iron 2 makes green and iron 3 makes brown. Now, if you remember that transition metals form coloured compound, which is content for paper 1 especially, then you'll remember that all the ones that are coloured are transition metals. So copper blue, iron 2 green and iron 3 brown. If, however, your unknown compound contains calcium, magnesium or aluminium, then a white precipitate will be formed. Because all of these are white, you'd need to do further tests to find out whether it's actually calcium, magnesium or aluminium you've got. Now, to determine if you've got aluminium or not, you can add sodium hydroxide in excess to the solution. And with aluminium, if you add excess sodium hydroxide, it turns colourless because the precipitate that you've just made dissolves back in the solution. So that will help you identify the aluminium. For the other two, you may need to do a flame test, and if it comes up as orange red, you know then you've got your calcium. To remember the difference then between these white precipitates, if you remember that calcium and magnesium are in group 2 and the aluminium being in group 3 is the one that does something different. Okay, so the group 3 one is the one that will disappear when you add excess sodium hydroxide. Now let's look at the test for anions, which are the negative ions. First of all, we'll look at testing for carbonates. So that's if the second part of your compound was CO3. So for this test, you would place a spatula of your unknown compound in a test tube and add dilute acid. So we'd have our unknown compound in the bottom and acid added on top. We then add a bung and delivery tube and connect to a test tube containing lime water. If carbonate ions are present, then carbon dioxide will be released and the lime water will turn cloudy like shown in the image there. If you had a negative result for the carbonates, you might want to then test to see if your compound contained a halide ion. And the three that you need to be aware of for your exam are chloride, bromide and iodide. So if you remember, halide ions are from group 7 of the periodic table where you find the halogens. So to test for these halides, you would add a few drops of dilute nitric acid and a few drops of silver nitrate. So for the chloride ions, first of all, I'll show you the ionic equation. The silver ions from the silver nitrate react with the chloride ions, if they're present, to form silver chloride. And if chloride ions are present, the silver chloride is a white precipitate. For the bromide ions, again, the silver ions would react with the bromide ions to make silver bromide, but this time that is a cream precipitate. And if iodide ions were present, that would form a yellow precipitate. Now, to help you remember, if you think about the periodic table, you can think of the precipitate getting darker as you go down the periodic table. So white precipitate for chloride ions, cream for bromide, and yellow for iodide. So if you've got negative results for carbonates and halides, you might want to finally test to see if you have sulfate ions in your compound. So to test for sulfates, you would have your unknown compound in a test tube, and you'd add some hydrochloric acid and some barium chloride. And if sulfate ions are present, a white precipitate will form, and this is because barium sulfate is being formed. So the barium ions from the barium chloride react with the sulfate ions, if they are present, to form barium sulfate.